You might be wondering, what does the artist Vincent van Gogh have to do with buck and boost converters? But to understand the buck and the boost converters, it helps to understand that a water wheel works exactly like a coil in electronics. So here we have a watermill. This one was painted by Vincent van Gogh about 100 years ago. But the watermill itself is much older. But physics are physics. They have been working since forever and will keep on working until forever. So the principles here are the same as the principles in electronics. It's the same physics in the end. The electronic equivalent of the water wheel is the coil. Behind the water wheel we see a small lake. The electronic equivalent of that is the capacitor. Let's walk to the other side. On the upstream side we have another lake, another capacitor. Here we see the water wheel. Sadly it's not turning today. And if we look closely, we also find the switch to turn it on and off. Down here, the gate. So the gate is turned off at the moment, so there's almost no water flowing. The gate is not perfect. And here's the controller for the gate. It sadly has a padlock on it, so we can't open it ourselves. If you would open the gate, the water would start flowing, and very slowly this huge water wheel would start turning. But as is clear, I'm sure it will start turning very slowly. It will take a little while for it to pick up speed, and it will never turn faster than the water is flowing. This water wheel does not work like a buck or a boost converter, but all the components are there. The water wheel is the coil, the big gate is the MOSFET or the switch, and we saw two capacitors, a reservoir before and a reservoir after the water mill. In reality, this one drives to milling things. On the one side they press linseed oil out of linseed, and on the other side they grind wheat into flour. But not today. It's much too cold and there's no tourists to look at it. Here's a little explanation about the water mill. And you can pause the video if you want to read it. In this video I will explain how a boost converter works. A boost converter and a buck converter both work in similar ways, but sort of different and opposite. There's a lot of nonsense going around and a lot of videos on YouTube explaining how it works that are not correct. Before with the water mill I explained that a water wheel and a coil are similar. So first I will explain it using liquids, and then we'll exchange the components for electrical components, and you will see that it all makes sense. So I've drawn my circuit here, or at least the beginnings of it. Yeah, we have a pipe going this way with a joint, and it's going there. Here we have a reservoir. This is a switch, and this is where the water comes in and it pours down to the ground. So you can imagine this as being connected to a tap, and if we open the tap, water will flow. In this situation it would just go down here to the ground. So let's build up our boost converter. I already installed the water wheel because that was the complicated part of the drawing. Here we are going to make a reservoir as a capacitor. So the best way to understand that is that we have a box and the water can come in, but we have a rubber balloon which will fill, and it will also give some pressure to push the water back out. Because the balloon is in a box, it cannot go bigger than the box. You will see the same thing if you have a central heating, at least here in Holland. The central heating will also have a usually red metal thing which has a rubber diaphragm in the middle to keep the pressure in the central heating system constant. It works exactly the same way. So we have our tap, a power supply, we have our coil, the water wheel, we have our switch, which is a switch. So we have to install a one-way valve. I was looking on the internet which kind of drawings exist for that. And one of them, to my surprise, looks very familiar. So that's the one we will use. So the valve goes here. This means that the water can flow this way, but it cannot flow back that way. So what happens if we open the tap? Water will flow here, down here, and down here, and out. There's no reason for the water to go sideways because flowing down and out is much, much easier. And it will flow here, creating a big puddle on the ground. The first thing you have to understand is that when the water starts flowing, the water wheel will turn. But the water wheel is big and heavy. You saw that with the watermill earlier. So you have to understand that when the water starts flowing, initially the water wheel is stationary and it will start turning, and slowly, slowly, slowly it will pick up speed. The maximum speed will be governed by the mechanics of the water wheel, but also by the flow rate of the water. The wheel cannot turn faster than that the water is flowing. But what happens when we close the switch here? If we close the switch very suddenly, the water can no longer flow out here, so the water flow will stop. But we have a problem. The water wheel is turning. Blocking the water here will cause the water wheel to stop eventually, but in the beginning the water wheel is still turning because it has a lot of mass, it has a lot of momentum, it is turning, and it is creating a high water pressure here. It is pushing the water down here, but it cannot go out, so the pressure here is going to be very, very high. The water can then escape sideways. The water can go this way through our valve, and now it can go up. Normally it would not flow higher than this point because that is where the water level is at. There's no more pressure than to go higher than here. But now the water wheel is pushing the water and it's forcing it all the way up and up and up, and it's going to fill our balloon here. But after a little while the water wheel has stopped and no water is flowing. Everything stops. So now we open the switch again. Water will start pouring this way again, causing the water wheel to start turning. And once the water wheel has picked up full speed, we suddenly close the switch again. Pressure builds up, pushing the water up and up and up and up, and filling our balloon or our capacitor. So you see that by opening and closing and opening and closing the switch, we cause the water wheel to pick up speed, create a high pressure momentarily, which has enough pressure to push all the way up and into the balloon. And so what we do to create a high pressure and fill the balloon with a high pressure water, we open and close the valve, on and off and on and off. When it is open, the wheel picks up speed. Energy is stored in the water wheel. The moment we close it, the wheel keeps on turning for a bit, creating a high pressure, which causes the water to flow and start filling the balloon. A little while later, the wheel has stopped. No water is flowing anymore, but the water from the balloon cannot flow back because there's a valve here. So we keep our high pressure water safe because of the valve. Then we open the valve again, the wheel starts turning. While the wheel is turning and this is open, no water is going this way because it's easier for it to flow out there. Then we close it again. Now the wheel, with the momentum it still has, creates a high pressure again, through the valve and into the balloon. A little while later the wheel has stopped. This is still closed, but because of the valve, the pressure cannot go back. Because of the magic of physics, we can replace these liquid components with electronic components, and mathematics are mathematics, so everything will keep on working the same way. This is not coincidence, but this is deeply fundamental that this works. So the tap, we get rid of, we connect this to our power supply. The water wheel we replace with a coil. The switch we replace with a switch, a MOSFET in our case. The balloon in our tank we replace with a capacitor. And our valve we replace with a diode, which magically already has the right symbol. So here we have the basic schematic of a boost converter. A coil, switch, diode, capacitor in this particular order. And it works in exactly the same way. Here we have our power supply, which sends a current through the coil. In the beginning, the switch is closed, so the current flows to ground. Then we suddenly open the switch. The coil, just like with the water wheel, the current through the coil cannot change abruptly. So when we turn on the voltage, the current starts flowing, but because the coil does its thing, the current will slowly increase from 0 to whatever. But in reverse, the moment that we close the switch here, we turn off the MOSFET, the current cannot go through the MOSFET anymore, but the current is continuing through the coil, at least for a little while, because it cannot stop abruptly. This current builds up a huge voltage here, which can flow through the diode and charge this capacitor. This voltage spike generated here, if you close this switch infinitely fast, the voltage here will be infinitely high. In reality, it isn't, of course, because you cannot close the switch infinitely fast, but we have a high voltage here. The voltage here will be higher than the voltage in the capacitor, so some current will flow and charge the capacitor. All we have to do is keep on turning on and off and on and off and on and off this MOSFET. So every time we turn the switch on, we turn the MOSFET on, a current will flow from the power supply through the coil to ground. This current starts at 0, but it increases and increases until the coil is saturated. At that point, or maybe earlier, you close this MOSFET, causing a huge voltage spike here, which goes through the diode and charges the capacitor. So we drive the gate of the MOSFET with a square wave, turning it on and off, and all the rest is automatic. Here we have a simple boost converter that I made to show the principle of a boost converter to my friends. Let me draw the schematic. So we have the coil, which is here. We have the diode. We have the MOSFET. To the ground. And the gate. And we have a capacitor, which is this big guy here. Also to the ground. This is our output. And it also has a voltage divider. This goes to the CPU. Here's our output. Then this goes to our 5 volts. The 5 volts comes out of our USB plug. And to drive the whole thing, we have a little microprocessor which basically only works as an oscillator in this case. It generates a square wave to drive the MOSFET. So here we have our microprocessor generating the square wave, and this feedback line also feeds back into the CPU. CPU is of course also powered from the same 5 volts. And as an added bonus, we have a LED with a resistor. So we have a LED with a resistor. That's also driven by the CPU. So when the voltage reaches a certain level, it turns on the LED. So again, what happens? When the MOSFET is closed, the current flows here to ground. Slowly the current increases through the coil. The coil is building up momentum. The water wheel is getting energy to turn. Yeah, it has momentum. The coil has energy as well, but it's stored in the magnetic field. The moment the switch is opened, the current cannot flow through the MOSFET anymore. A huge pressure builds up here, a high voltage builds up here, gets pushed through the diode into the capacitor, which is charged. A little while later, you close the MOSFET again, the current can flow here, and this current, the voltage from the capacitor, will not flow back through the diode because the voltage here is much higher than the voltage here when the MOSFET is closed. So in the case of my little board here, let me zoom in on it. The CPU, the LED with the resistor, our MOSFET, the coil, the diode, the capacitor, and 2 resistors for the voltage divider. This resistance has 100 times bigger resistance than that one, so all the voltage is here. So this is a high voltage resistor. So the CPU is here. It makes the square wave of around 100 kilohertz. It drives the MOSFET. All this charge is built up in the capacitor. From the way this is dimensioned, we get about 300 volts on the capacitor, and we put it on the ring there. And the ring on the other side, they're not connected, the two. The ring on the other side is connected to the ground. So we call it the USB killer revenge. Yeah, because some people create similar devices that create a high voltage that goes into the data lines of the USB to kill your computer. But this doesn't kill the computer. It puts the high voltage on the ring. So if you touch it to pull it out of your port, the poor user gets zapped. But the coil is very small. The capacitor does not have much capacitance, so the actual current is not very big. So you'll feel it, you notice it very, very clearly. And you might even jump, but it's not dangerous. And the moment you touch it, you're discharging the capacitor and all the voltage is gone immediately.
Aral, ¿cómo estás? Voy a usar tu herramienta. Acá. Y ahí que me...
Ahora sáquela, retírela, de ahí mismo agarradita.
Ay, no sé por qué están mal dado.
So I hope that you now understand how a boost converter works, that it is not magic, but simply physics or electronics at work, and that you can think of a coil as a water wheel. So we started out by showing you the painting of Van Gogh, who painted the watermill. Van Gogh probably didn't know anything about electronics, but ironically he did cycle through the same street where we have our office. He must have cycled there many, many, many times. But that was before our time. I hope you now understand how a boost converter works. In my next video, I'll explain how a buck converter works. It works much the same way. It is slightly more difficult to understand. That's why I did this one first. So please subscribe to our channel so you don't miss out on that one. If you enjoyed this video, please like it. And if you like our products, please visit our website, www.cmizapper.com. Thank you for watching.
Como si fuera...
Sí, agárrala a sacarla, trata de sacarla.
Ah.